Okay, so our next speaker is Joe Moeller. Joe, are you there?
Yeah.
All right, so Joe is going to speak about Petri nets with catalysts. Yeah, go ahead.
Okay. Okay. So, right. My name is Joe, and I'm going to speak about Petri nets with catalysts. And so this is based on a paper that I wrote with my advisor, John Baez, and another collaborator, John Foley. And just like Jade, I'm a student of Baez and also graduating this year and going to be on the job market very soon. So, and I also wanted to acknowledge that I did this work while living on Kauai land and working on Tongva land. Okay, so I'm not the first or the last person who's going to talk about Petri nets in this conference, but I think I'll try to give my own version of an introduction to them to begin with. Just because if you aren't familiar with Petri nets, then perhaps seeing multiple different perspectives on it will help it stick in your mind a bit. And also I'm gonna sort of build on top of my particular presentation of it to get to the stuff that I actually did here. So this is what Petri net looks like. So there's two types of nodes in this graph. And the blue ones here are a process that uses up some stuff that's coming out of the yellow ones. The yellow ones are like a resource. So you have a resource or a bunch of resources, and then a bunch of processes that have particular resource dependencies, and you just draw a picture of it. And so these were originally motivated by chemistry, and so you could imagine that these resources are particular chemicals, and then the transitions or processes are reactions that use those particular resources. And there's a thing called the token game that you can play on a Petri net, which is that you actually imagine that you have certain amounts of these resources. And then you can ask yourself, what exactly can I do with these processes with the given amount of resources that I have to start with. So for instance, I wrote down 2A plus 1B, and I should have labeled these like A and B and C, but I think you can see that there's 2 here and there's 1 here, so this is A and B. And so this is like, whatever these resources are, you have 2 of one of them and 1 of another. And then you can see like what sequence of processes are you allowed to execute with this starting point. Right, so if, for instance, I wanted to run the process tau1, I wouldn't be able to because it would depend on having some amount of resources from C, and so I can't do that, but I can do tau1 because it asks for 1 of A and 1 of B. Should have said also that these arcs that connect yellow to blue are supposed to represent the amount of tokens that it takes to run this process. So this is 1 and 1. And then tau2 would take 1 of this and produce 2 of this. But let's see what would happen if I did tau1. So if I execute the process tau1, then it would take 1 from A and 1 from B and spit out 1 in C. And so that's exactly what happens here. And so I'm going to call that an execution of one of these processes. And you can write it down like this, that you started with this amount of tokens and you executed tau1, executed the process tau1, then it'll land you in having this amount of all of the resources. And you can do multiple processes sequentially, right? So if I do the one that I just described, then I end up here. Now I do have enough resources to run tau2, and so I can do that again, or I can do tau2 and end up somewhere different than where I started, and this is what it looks like. And so this is what we're going to use as the morphisms in a category that we're generating from this Petri net. So we call this Petri net. If we call this Petri net P, then the category that I'm building here with these sort of pictures of executions of this token game is going to have objects that are these markings, which are amounts of resources. The morphisms are going to be sequences of executions, right? You can't just be a single execution, because if you do multiple, you have to be able to compose them. So we take sequences of executions of processes to be the morphisms, and you compose them just by concatenation, meaning like you did a bunch of, you executed a bunch of processes and then you executed a bunch more, then sticking those two sequences together gives one long sequence. So we call this FP, for like free on P. But there's something else you can do here. In the top left marking of this Petri net, I have enough resources. This marking is specifically, I made it specifically to have enough resources to run either tau1 or tau2. And in particular, if I ran tau1, I would still be able to run tau2. Or if I ran tau2, I would still be able to run tau1. So that's what I'm doing along the sides of this square. And it ends up in the same place. That if you did tau1 first, you took these two tokens and produced one in C, and then you ran tau2 and it put 2 back into B. Or if you did it the other way around, then the result is the same. And so then this square is commuting, and this is going to be what we mean by doing these processes in like concurrently. So this is supposed to be a model. One way that people use Petri nets is as a model of concurrent computation, and this is where the concurrency is sort of naturally arising. So we can represent this by saying this is tau1 plus tau2, like the overall thing that you would get by doing either of these sequences is called tau1 plus tau2, and it starts here and ends here. And so in particular, we can say that this is going to give us a monoidal structure on the category FP, and moreover, it's commutative, as Jade was talking about before. Okay, so whenever you have a monoidal category, at least to an applied category theorist, probably the first thing that you should ask yourself is, what do string diagrams give me for this category? And so this is how you would get, this is what the string diagrams for a particular Petri net are going to look like. So here's this Petri net that we've been using for the whole time so far. And these are like the basic building blocks for what all the string diagrams of morphisms in the category FP are going to be. And so these just look exactly like the two transitions in the Petri net, sort of cut off from the Petri net itself. And I'm reading from top to bottom. I always read from top to bottom for my string diagrams. And you can see that it's like coming from A and B and going to C. And so that's exactly what these pictures do. Tau2 goes from C to 2 copies of B. So for instance, here's one particular morphism in FP represented in these string diagrams. So I'm reading from, like I said, top to bottom. And this is like saying I have 4 tokens in A and 1 token in B. And here's a particular way that I can turn that into 2 Bs, a C, and an A. And I built it up just completely from sticking together these basic building blocks. Right. So the sort of main thing I'm talking about adding to this idea about Petri nets is a catalyst. So a catalyst, drawing from chemistry, again, a catalyst is something that's like involved in a reaction, but doesn't actually get consumed by the reaction. I guess there's might be different ways of saying exactly what a catalyst is and what it contributes to a reaction, but in the way that I'm going to use it, I'm going to say that it's something that is neither consumed nor like increased, produced by a reaction. And so in particular, you could say that as, you can express that as saying that the in degree and out degree of a resource is the same whenever you look at a particular transition. So in this example, this top resource is going to be a catalyst because the in degree and out degree with respect to tau 1 is 1, like they're both 1, and with tau 2 it's both 0. So nothing that you can do in this Petri net is going to either increase or decrease whatever amount you started with in this, whatever this top resource is. And so you can modify the string diagrams that we're using for the category FP a little bit to sort of reflect or like keep track of this idea that you're not supposed to create or destroy any of whatever this thing was. So now I give it a label A, and so I'm going to color the string of a catalyst red all the time now. So for instance, in this Petri net, if you started with an A and 2 Bs, then here's one morphism, here's one sequence of executions you could do in this Petri net that would result in 2 Cs and an A. So the A does not change amounts throughout this whole thing, even though B and C do. Yeah, so the red is just to keep track of it. And so here's an example. So I started in this one with an amount of tokens at the top representing like how much you start with, and then here's an amount of tokens that you might want to end with. And then this sequence like performs that transition for you. But if you have here's a different starting point and ending point that you could imagine, and there's one token of the catalyst to begin with, and it ends with 2 tokens of the catalyst. And like I've been saying, you can't change the amount of catalyst, because that's what it means to be a catalyst here. So nothing fills in this. There's nothing I could draw here that would properly fill it out. And so what can you conclude about that? You can conclude that there's a whole bunch of objects in this category which have absolutely no morphisms between them. And if you think about it, that sort of makes you think that the category is like a bunch of islands, a bunch of completely disjoint pieces. And so that's exactly what we get in this scenario, that if you have a Petri net and you have some catalysts in it, it could be more than one catalyst. I've only been drawing Petri nets with exactly one catalyst, but you could have multiple catalysts in it. Then it actually tells you that your category FP is a disjoint union of a bunch of other categories. And each one of those corresponds to a fixed amount of catalysts that you start with. And every marking that you can get from there is going to have the same amount of catalysts. And so those are a bunch of subcategories that are completely disjoint from each other, morphism-wise. And it's sort of overkill initially. It might seem like overkill to say, well, okay, I've got a bunch of disjoint, I got a disjoint union of a bunch of categories. That's an op vibration of the category. But it's going to be useful for what I'm going to say next. So I'm just pointing out that like if you have a disjoint union of a bunch of categories, then that's in a very trivial way a fibration and an off vibration. And in particular, this is a monoidal vibration because this is, we get this monoidal functor down to this category, which I haven't mentioned yet, but it's the free monoid free commutative monoid on the set of catalysts. But let me say more about the growth and deconstruction before I move on. So I'm talking about fibrations, and when you talk about fibrations, you should talk about the growth and deconstruction. So a sort of classic theorem is that the growth and deconstruction gives you an equivalence between these two things, fibrations and index categories. And this isn't a talk about the growth and deconstruction specifically. I'm just going to use it, so I'm just sort of reminding you and giving you a picture of what's going on. But I did give a talk about it at the MIT seminar a while ago. So you could probably find a video of that if you wanted to, but this is what fibrations look like when I picture them, and this is what index categories look like when I picture them. And something that Christina Vasilikopoulou and I did, and sort of builds on some work of Mike Schulman, is that we sort of figured out a monoidal version of this. And in particular, if you have a co-Cartesian base, then monoidal op fibrations over it are going to be the same as op indexed monoidal categories. So that means that if you have this total category, which is monoidal, you have a monoidal fibration, and this is Cartesian or co-Cartesian, then that means that you can induce monoidal structures on all of these subcategories. That's what I mean by putting this little red tensor on everything. So what does that mean for our situation? Means that these subcategories should have a monoidal structure. Actually, it doesn't mean that because we don't have a co-Cartesian base. But we can try. We can still look around and see what we get, right? So these subcategories, they're not closed under the tensor product. So if you try to add two processes that have one token of the catalyst, then they don't end up in that subcategory, right? So it's not closed under this monoidal product, but you generally don't really expect that from a subset of like an algebraic thing. You don't expect it to be closed under the operation. But this monoidal growth and deconstruction thing is sort of saying maybe you can still induce one by like playing around with it a little bit. And there's sort of an obvious way that you can like think about turning this, like fixing this picture. You have two red tokens over here, and if you had enough resources to run tau1 and tau2 separately, but you only have one token of A, you'd still be able to come up with something. What is it? You just reuse.
Do you think you can wrap up in 2 or 3 minutes?
Yeah, sorry. Yeah, okay, so you reuse that token, and it gives you this thing that's like a tensor product, but it's only going to be pre-monoidal because you can't slide these two things around freely. They're restricted by their dependency on using the same token. This actually gives us a something that looks sort of like a combinatorial species, but where all these things have a pre-monoidal structure on them. And I think I'll stop there, just say that you get pre-monoidal structures on all of these. Yeah, maybe I'll just stop there.
Okay, great. Yeah, thanks so much.
Yeah.
All right, so yeah, we have a few minutes for questions. There has been some discussion in the chat, starting with, I'm not sure if this has already been answered. Cole Comfort is asking, are catalysts related to particle-style traces?
I don't know. I've never heard of that.
Maybe Cole, do you want to clarify? Is this about traced monoidal categories?
Yeah, I think maybe I just don't know what I like didn't fully understand what what's it called, a catalyst was in this context. That's all.
So catalyst is this, so maybe your question is like, what is the motivation for talking about a resource that doesn't get consumed or produced in a process? If that's the question, then like our motivation was actually thinking about a sort of network of resources, but like where your resources can be like trucks and boats and people and maybe like warehouses full of boxes of stuff. And you want to transport these things around, but you want to also keep track of the resources you're using to do certain things. So like, for instance, a truck, if you ignore like wear and tear and gasoline and stuff like that, then a truck is sort of a resource that doesn't really get depleted by the process of transporting something from point A to point B, but it is a resource that you have like in a limited amount, and you still have to keep track of like the use of your trucks. And so that's what I was thinking of initially while coming up with this. I don't know if that makes.
Yeah, thank you.
Yeah.
Okay, yeah, if there are more questions, feel free to speak up.
Yeah, so hi Joe, very nice presentation. So I guess the first half of my question was already answered, kind of where the inspiration came from and maybe applications. I was particularly interested in the, potential application towards actual chemistry. And I'm just wondering, so it's a general question, I'm just curious now. Would you think it's an easy extension to include things like reaction rates this is, I guess, more general to Petri nets, but to catalysts, it might be particularly interesting. I'm asking because even in the examples you mentioned, let's say you have branching paths or something like that. If one reaction rate or rate of transfer, however you call it, is much higher, then, and this happens in actual chemical networks, is that it basically makes the other branch futile. So you actually never see reactions, or, statistically there might be something there, but nothing meaningful on the, let's say, bottlenecked branch. So anyway, not to drag on too long, what are your thoughts on this?
Yeah, that's a really interesting idea. I think that, there's already been something about doing like, I guess, a more stochastic version. Mine is like very the way that I've been working with Petri nets is like sort of very discrete, I guess. And there's been other work that like fits into the same sort of categorical framework that treats things, I guess, stochastically. And so like the work of like Pollard and I don't remember like the exact names on the paper, but so John Baez and then Blake Pollard, and I don't remember if Brendan Fong was on the particular paper that I'm thinking of, but it was all around the same time.
It was just Blake.
Okay, it was just Blake.
I
don't remember sorry, but yeah, there's been work like that. And
I'll just interrupt and say chemists have been working on Petri nets with rate constants attached for a long time and have lots and lots of nice theorems about them.
Okay, interesting. Thank you.
Yeah, but it's like in the same framework, so it could be sort of easily combined. I think it wouldn't take like a ton of work to combine these two aspects.
Sure. Cool. Thank you.
Yeah.
So, I noticed your catalysts have to be catalyst with respect to all the reactions. But in like biological systems, you get reactions that create catalysts for other reactions. How does that fit into this framework?
So we didn't consider that at all. Like we acknowledged that it's like a clear thing that should happen in examples that you consider, but we set that aside for future work, I guess. But like sort of the first thing that comes to mind when I think about that is that probably open Petri nets is like a good place to start thinking about that, because you could have maybe like an open Petri net that has a catalyst in the way that I've defined it, but it's also part of like maybe a big composite Petri net that you get from thinking about open Petri nets, where maybe other parts of that Petri net actually don't treat it like a catalyst in the way that I've said, that particular resource.
Right.
That'd be like the way that I would start thinking about that.
Mm-hmm. Right. You could have it would be a catalyst. You could have a catalyst that is also an input, and thus another reaction could produce it for you.
Right. Exactly.
Okay. That makes sense. Thank you.
Yeah. So maybe you're sort of like cutting out a small piece where it acts like a catalyst, and then the rest of it, it's just a general resource.
Okay, so I think we should move any further discussion to Zulib. But yeah, thanks again, Joe.
Yeah.
For very nice presentation.